Alrighty, I'm going to be talking about why it might make sense to rename the dark energy spectroscopic instrument to the oversized optical depth spectroscopic instrument, or OOPSI for short. Okay, so how do we go from DESI to OOPSI? Well, as Satya mentioned in her very nice overview of DESI, that the DESI data on their own are perfectly consistent with lambda CDM, just with a slightly lower matter fraction than what we get from the CMB. Okay, so how does the optical depth fit into this? Well, the matter fraction that we infer from the CMB, and here what I mean by CMB is high L CMB, meaning L greater than 30, and then also CMB lensing, is negatively correlated with the optical depth. Okay, and this is due to lensing. So the primary CMB measures AS times e to the minus 2 tau. Lensing measures some combination of AS and omega matter, and so kind of if you divide those two amplitudes, you get this correlation here. Okay, now the way this degeneracy is broken in the CMB is through large-scale polarization data. There's this so-called reionization bump that's proportional to the optical depth squared in the EE power spectrum. And this reionization bump is due to quadrupole anisotropies that are horizon scale size at the time of recombination, or sorry, at the time of reionization. So this is very large scale, so something like L of 5 or something like that. And the way that tau is inferred from this reionization bump is relatively insensitive to the model that you have of reionization, which is a very nice feature of inferring the optical depth from low LEE. However, on these extremely large scales, the E-mode power spectrum is more than 2 orders of magnitude smaller than that in temperature. And at the same time, you also have both polarized galactic emission and also, the same kind of instrumental effects, so nonlinearities in your analog to digital conversion, or T2P leakage, or beams, well, beams don't really matter. But anyway, that's to say the systematic errors are comparable to what you have in temperature, but the signal is 100 times smaller. So it's much easier to get a systematic error here than in temperature. And another sociological point, less of a scientific one, is that we really only have 2 independent measurements of this large-scale polarization. We have WMAP and we have Planck. And something that's interesting about these measurements is that they've been monotonically decreasing over time. So initially tau is 0.16 or something, and then settled around to 0.19 or so, 0.09. And then with the latest Planck data, prefers a smaller value. Okay. So one question that you could ask is what should tau be, at least within lambda CDM, using data that is statistics limited rather than systematics limited. And so here the data that we're including is, again, the small scale CMB, where by small, it's not actually that small, it's L greater than 30, CMB lensing, and then also BAO data.
Yeah, I think you're right. Doesn't say that.
It's okay?